Hello and welcome. Today, we're diving into the fascinating world of advanced prosthetics, artificial limbs that are becoming less like tools and more like true extensions of the human body. How is this happening? A major key lies in how we control them, specifically by listening to the body's own signals. At the heart of this revolution is myography, especially electromyography, or EMG. Every time you decide to move a muscle, your brain sends electrical signals down to it. EMG technology uses sensors, often placed on the skin over the remaining muscles in a limb after amputation, to pick up these incredibly faint electrical whispers. In traditional prosthetic systems, these signals acted like simple switches. Contract muscle A to open the hand. Contract muscle B to close it. Useful, but limited. But technology hasn't stopped there. Modern prosthetics are much smarter. Imagine instead of just on/off signals, we could interpret the touch patterns of muscle activity. Thanks to sophisticated algorithms and machine learning, systems can now analyze complex EMG signals from multiple muscles at once. This allows users to control their prosthetic arm or hand much more intuitively. Think about making a fist or rotating your wrist. You don't consciously trigger individual muscles in sequence, you just think the movement. Advanced EMG aims to capture that intent, translating natural muscle activation patterns into complex movements, like individual finger control or varying grip strength. To make control even more reliable and intuitive, engineers are combining EMG with other types of sensors. This is called sensor fusion. Inertial sensors, like those in your smartphone, can track the limb's position, helping the system understand if a muscle signal is an intentional command or just part of moving the arm around. Other techniques measure the tiny vibrations muscles make when they contract, or even use ultrasound to see how the muscle changes shape. For even clearer signals, sensors can be implanted directly into the muscles or near nerves. This bypasses interference from skin and tissue. A remarkable surgical technique, called targeted muscle reinnervation, or TMR, actually reroutes nerves that once controlled the lost limb to remaining muscles. This creates more natural signal sources for the prosthetic, allowing for potentially even more intuitive control. What does all this advanced tech achieve? The goal is a seamless connection between thought and action. By combining different sensor data and using smart algorithms, these systems learn the user's unique muscle patterns. This means less mental effort is needed to control the limb. Users can focus on the task, not the mechanics. Movements become smoother, more natural, mimicking biological limbs. It unlocks greater functionality for daily life. Researchers are even working on ways to send sensory information, like touch or pressure, back to the user, creating a true feeling of embodiment. Of course, challenges remain. Keeping signals stable over time, managing the complex computations, making sensors durable, and ensuring these amazing technologies are affordable and accessible are all hurdles we still need to overcome. But the future is incredibly bright. Refining sensor fusion, improving machine learning, developing better implants, perhaps even directly connecting with bone and nerves, and closing that sensory feedback loop promise prosthetic limbs that function almost indistinguishably from natural ones. We're steadily blurring the lines between the artificial and the biological, offering incredible new possibilities for people living with limb loss. Thanks for tuning in.